Section 1 Introduction. We are delving into the subject of single image 3D reconstruction, a significant and challenging problem in the field of computer vision. The task entails creating a three-dimensional model from a single two-dimensional image, which is vital for various applications including robot manipulation and navigation, 3D content creation, and augmented or virtual reality, AR, VR. The difficulty lies in reconstructing not only the visible parts of the object but also the unseen areas, often leading to multiple plausible solutions due to the inadequate information provided by a single image. Humans are adept at visualizing unseen 3D content, drawing from our extensive knowledge of the 3D world. To equip artificial intelligence with this capability, many techniques utilize class-specific information by training 3D generative networks on 3D-shaped databases. However, these techniques often struggle when encountering unknown categories, and their ability to reconstruct is limited by the size of publicly available 3D databases. In our research, we strive for a generic solution that can convert an image of any object into a high-quality 3D textured mesh. We propose a novel approach that leverages the powerful knowledge learned by 2D diffusion models for 3D reconstruction. Given the greater accessibility and scalability of 2D images, recent 2D generative models like DALL-E, Imagine, and Stable Diffusion have made substantial progress by training on large internet-scale image databases. By combining these models with 3D tasks, we aim to further enhance their capabilities. Indeed, research such as Dreamfield, DreamFusion, and Magic 3D has begun to utilize 2D diffusion models to assist 3D generative tasks. Despite the successes of these optimization-based methods, they encounter several common challenges. They are time-consuming and memory-intensive, often generate 3D inconsistent shapes, and struggle to extract high-quality mesh from good RGB renderings. To overcome these issues, we propose a unique approach that employs 2D prior models for 3D modeling. Our method combines a 2D diffusion model with a cost-volume-based 3D reconstruction technique to create a high-quality, 360-degree textured mesh from a single image in a feed-forward pass without precision optimization. We utilize a recent 2D diffusion model, 0123, fine-tuned on Stable Diffusion, to generate multiple perspectives of the input image. However, there are challenges associated with reconstructing from synthesized multi-view predictions such as lack of consistency within multi-view predictions and the necessity of the camera pose of the input image. To tackle these challenges, we build upon a cost-volume-based neural surface reconstruction approach, sparse noose. We also introduce several training strategies and an elevation estimation module that estimates the elevation of the input shape. This data is used to compute the required camera poses by the reconstruction module. Our integrated method of multi-view synthesis, elevation estimation, and 3D reconstruction can create 3D meshes of any object from a single image in a feed-forward manner, reconstructing 3D shapes in significantly less time and providing better geometry and more consistent 3D meshes. Our reconstruction adheres more closely to the input image compared to existing methods. Our method was evaluated on both synthetic data and real images and demonstrated superior performance in terms of both quality and efficiency compared to existing methods. Please refer to the attached figure for some of our example results. Section Summary. Single image 3D reconstruction is a challenging task that involves reconstructing a 3D model of an object from a single 2D image. Existing methods often rely on class-specific priors and 3D generative networks trained on limited 3D-shaped datasets, which limits their generalization to unseen categories. In this paper, we propose a novel approach that leverages the strong priors learned by 2D diffusion models to turn any object image into a high-quality 3D textured mesh. Our approach combines a 2D diffusion model with a cost-volume-based 3D reconstruction technique, enabling the reconstruction of a 360-degree textured mesh from a single image in a feed-forward pass without precision optimization. Section 2 Related Work. Let's look into recent developments in related work. Section 2.1 covers 3D generation driven by 2D prior models. We've seen a rise in 2D generative models like DALL-E, Imagine, and Stable Diffusion, as well as vision language models like CLIP. These models were trained on vast internet-scale image datasets, developing a vast understanding of visual concepts. These models have been incredibly useful because they have a great understanding of our 3D world based on 2D data. A variety of research has been inspired to use these 2D models to aid 3D generative tasks. Notable examples include Dreamfield, DreamFusion, and Magic 3D, which use a model where each shape is optimized individually. These models work by optimizing a 3D representation, such as Nerf, Mesh, or the SMPL human model, and use a process known as differentiable rendering to create 2D images from various angles. These images are then evaluated using the clip model or 2D diffusion model to compute the loss functions, which in turn help optimize the 3D shape. In addition to this, some work trains a 3D generative model using the clip embedding space, while others focus on creating textures or materials for input meshes using the 2D model's prior understanding. Section 2.2 discusses the process of converting a single image into 3D. Prior to the advent of clip and large-scale 2D diffusion models, 3D priors were usually learned from synthetic 3D data or actual scans. Unlike 2D images, 3D data can be presented in various formats, leading to a wide range of 3D generative models specific to these different representations. These models use a combination of a 2D image encoder and 3D generators to create 3D data in multiple forms, including 3D voxels, point clouds, polygon meshes, and parametric models. There has been an upswing in work on learning to generate a 3D implicit field from a single image. Several works are utilizing 2D diffusion models for per-shape optimization, which allows text to 3D tasks given that these models are often conditioned on text. To generate 3D models from a single image, some research has made use of textual inversion. This process finds the text embedding that best matches the input image, which is then fed into a diffusion model. Neuralift 360, for instance, includes a clip loss to ensure the rendered image resembles the input image. 3Diffuse fine-tunes the stable diffusion model with LoRa layers and a sparse depth injector to maintain stronger 3D consistency. 0123, a recent work, fine-tunes the stable diffusion model to create a new view of the input image based on the relative camera position. In addition to these methods, OpenAI has developed a 3D native diffusion model, Point E, that generates point clouds using several million internal 3D models. They also recently released another model, SHAP-E, which generates parameters of implicit functions that can be used to create textured meshes or neural radiance fields. Section summary. Recent research has focused on using 2D generative models and vision language models, such as DALL-E and CLIP, to assist in 3D generative tasks. These models optimize 3D representations and utilize differentiable rendering to generate 2D images, which are then used to guide the 3D shape optimization. Additionally, there has been work on generating 3D models from a single image by leveraging textual inversion and adding clip loss to enforce similarity between the rendered image and the input image. Section 2.3 Generalizable Neural Reconstruction. Let's delve into the process of creating more adaptable neural reconstructions. The traditional approach, like those seen in neural radiance fields, NERF, employs a neural network to depict a single scene, necessitating optimization for each individual scene. However, some methods attempt to learn common features across multiple scenes and apply them to new, unseen ones. These methods usually use a few source views as inputs, leveraging 2D networks to extract 2D features. These pixel-level features are then projected into the 3D realm, and a NERF-like rendering procedure is used on them. This allows these methods to create a 3D implicit field using only a few source views, all in a single forward pass. Various techniques are employed among these methods. Some directly combine 2D features using multilayer perceptrons, MLPs, or transformers. Others intentionally build a 3D feature or cost volume and use the voxel feature to decode the density and color. Beyond the density field representation, methods like sparse noose and volume recon implement signed distance function, SDF, representations for reconstructing geometry. Moving to our method, it can be visualized as shown in the included figure. We introduce a view-conditioned 2D diffusion model named 0123. This model generates multi-view images. We then highlight that traditional NERF-based and SDF-based methods often fail to construct high-quality meshes from inconsistent multi-view predictions, even when given precise camera positioning information. Hence, we propose a cost-volume-based neural surface reconstruction module that can be trained to manage inconsistent multi-view predictions and reconstruct a 3D mesh in a single forward pass. Our method builds upon sparse noose and introduces several vital training strategies to support 360-degree mesh reconstruction. Additionally, we illustrate the importance of estimating the pose of the input view in 0123's standard space for 3D reconstruction. While the azimuth and radius can be freely specified, we propose an innovative module that uses 4 nearby views generated by 0123 to estimate the elevation of the input view. Section summary. Traditional NERF-like methods require per-scene optimization and cannot generalize to novel scenes. However, some approaches use 2D networks to extract features from a few source views, unproject them into 3D space, and apply a NERF-based rendering pipeline to generate a 3D implicit field in a single feed forward pass. Our proposed method introduces a cost-volume-based neural surface reconstruction module that can handle inconsistent multi-view predictions and reconstruct a 3D mesh, while also estimating the pose of the input view for accurate 3D reconstruction. Section 3.10123, View Condition 2D Diffusion. In this section, we delve into the concept of 0-123 feet, which is a view condition 2D diffusion approach. To clarify, recent advancements in 2D diffusion models have revealed their capacity to understand a broad array of visual concepts. These models acquire strong priors by learning from data collected on a massive scale from the internet. Historically, such models primarily concentrated on generating images from text, but recent research has indicated that we can fine-tune these pre-trained models to add various condition controls. This process allows us to produce images based on particular circumstances. Conditions like canny edges, user scribbles, depth, and normal maps have shown to be effective. Building upon this, 0-123, a recent innovation, aspires to introduce viewpoint condition control into the stable diffusion model. More specifically, given a single colored image of an object along with a relative camera transformation, 0-123 aims to guide the diffusion model to produce a new image based on the altered camera view. To accomplish this, 0-123 fine-tunes the stable diffusion model using paired images and their corresponding camera transformations, which are derived from an extensive 3D dataset. As part of the fine-tuning dataset creation, 0-123 presumes that the object of interest is at the origin of the coordinate system and uses a spherical camera. This means that the camera is situated on the surface of a sphere and constantly focuses on the origin. For two camera positions, described by three parameters each, polar angle, azimuth angle, and radius, the relative transformation between these two positions is calculated as the difference in these parameters between the two positions. The ultimate goal here is to develop a model that can generate an image that closely resembles the appearance of an object from a different viewpoint, given the image of the object from one viewpoint and the transformation parameters to the new viewpoint. What makes 0-123 remarkable is that this fine-tuning process allows the stable diffusion model to develop a universal mechanism to control camera viewpoints. This mechanism even works for objects not included in the fine-tuning dataset. Section Summary. The recent work 0-123 aims to add viewpoint condition control to the stable diffusion model by fine-tuning it on paired images with their relative camera transformations. By assuming that the object is centered at the origin and using a spherical camera, 0-123 learns a model that can synthesize new images under transformed camera views. This fine-tuning enables the stable diffusion model to learn a generic mechanism for controlling camera viewpoints beyond the objects seen in the training dataset. Section 3.2 Can Nerf optimization lift multi-view predictions to 3D? In this study, we seek to determine whether Nerf optimization can uplift multi-view predictions into a three-dimensional representation. We focused on using a model known as 0-123 to generate multiple perspectives of an object from a single image. However, the question was whether we could use traditional Nerf-based or signed distance function (SDF)-based techniques to recreate high-quality 3D meshes from these predictions. To test this, we devised an experiment where we first generated 32 multi-view images from a single image using 0-123. These images were obtained from various angles, much like camera shots from different positions on a sphere's surface. Next, we processed these images through a Nerf-based method called TensoRF and an SDF-based method called Noose, both designed to optimize density and SDF fields, respectively. The results of our experiment were not as successful as we had hoped. Both TensoRF and Noose failed to deliver satisfactory outcomes, causing many distortions and floaters. We traced back this issue to the inconsistency of 0-123's predictions. The general fidelity of 0-123's predictions to the original images wasn't high, especially when we were dealing with extreme angles. However, the overlap of predicted and actual object regions, greater than 0.95 in most cases, and similarity to the original image from a high-level perspective were reasonably good. Despite this, the inconsistencies were significant enough to hamper traditional optimization-based methods. 0-123's original paper proposed a method for enhancing its multi-view predictions, but we found this approach to be imperfect and time-consuming as well. Moving away from optimization-based techniques, we used a flexible SDF reconstruction method known as sparse Noose for our reconstruction module. Sparse Noose, a variant of the MVS Nerf pipeline, combines multi-view stereo, neural scene representation, and volume rendering. Our reconstruction module, as illustrated, inputs several source images and their corresponding camera positions and outputs a textured mesh in a single forward pass. This module works by first extracting 2D feature maps from the source images. These features then contribute to a 3D cost volume, which further undergoes processing to obtain a geometry volume. This volume is essential for encoding the geometry of the input shape. To predict the SDF at any 3D point, a multilayer perceptron (MLP) network takes the 3D coordinate and its related interpolated features from the geometry volume. For color prediction, another MLP network takes the projected 2D features, interpolated geometry volume features, and the viewing direction of the query ray relative to the source images. An SDF-based rendering technique is then applied for the final RGB in-depth rendering. We also implemented a two-stage source view selection and a training method that combines ground truth and predicted data. We trained our reconstruction model on a 3D object dataset while keeping 0-123 constant, applying a spherical camera model for training shapes. For each shape, we first rendered ground truth RGB and depth images from various camera positions placed uniformly around the sphere. For each of these views, 0-123 was used to predict 4 nearby views. We combined these predictions with ground truth poses into the reconstruction module for training, randomly selecting one of the ground truth images as the target view. This two-stage view selection strategy proved essential for optimal model training, providing both RGB and depth value supervision. It allowed the model to handle the inconsistent predictions from 0-123 and reconstruct a consistent 360-degree mesh. However, during the inference stage, the ground truth renderings can be replaced with 0-123 predictions, eliminating the need for depth input. We demonstrated in our experiments that this mix of ground truth and predicted data during training is vital. Finally, to export the textured mesh, we used marching cubes to extract the mesh from the predicted SDF field and queried the color of the mesh vertices. Although our reconstruction module was trained on a 3D dataset, it mainly relied on local correspondences, showing excellent generalizability to unseen shapes. Section summary. The authors investigate whether traditional Nerf-based or SDF-based methods can reconstruct high-quality 3D meshes from multi-view predictions generated by 0-123. However, these methods fail to produce satisfactory results due to the inconsistency of 0-123's predictions. Instead, the authors propose a reconstruction module based on a generalizable SDF reconstruction method called sparse noose, which takes multiple source images with corresponding camera poses as input and generates a textured mesh in a single feed forward pass. Section 3.4 Camera Pose Estimation. Our reconstruction process requires knowing the camera positions for the images, which we refer to as source view images. In this context, we use the 0-123 method for image creation, which arranges cameras based on spherical coordinates, elevation, azimuth, and radius, labeled as theta, phi, and r, respectively. While we have the freedom to adjust the azimuth angle, phi, and radius, r, for all source view images at the same time, which would cause the reconstructed object to rotate and scale accordingly, this arrangement requires us to know the absolute elevation angle, theta, for at least one camera. This is to establish the relative positions of all cameras within a standard XYZ frame. To illustrate this further, the relative positions between two cameras will vary depending on the initial theta value, even if the change in theta and phi are the same for both. Because of this, any modification to the elevation angles of all source images at the same time, for example, adjusting all by 30 degrees upward or downward, could distort the shape that we're reconstructing. Hence, to avoid this issue, we have proposed a module to estimate the elevation angle of the input image. We first employ 0-123 to predict 4 views of the input image that are near to each other. Then, we methodically go through all possible elevation angles, beginning with a broad range and then refining the values. For each candidate elevation angle, we figure out the corresponding camera positions for the 4 images. We then compute a reprojection error for this set of camera positions to check the compatibility between the images and their respective camera positions. The elevation angle which results in the smallest reprojection error is chosen to generate the camera positions for all source view images. The method we use to calculate the reprojection error for a set of posed images is explained further in our supplementary information. In terms of implementation, for each input image, we create 8 images with camera positions that are evenly distributed on the surface of a sphere. For each of these 8 views, we generate 4 local images, each separated by 10 degrees, leading to a total of 32 source view images to be used. For reconstruction. During the training process, we keep the 0-123 model static and focus on training our reconstruction module using the Objaverse LVIS dataset. This dataset contains 46,000 3D models spread across 1,156 categories. We employ Blender Proc to generate the true RGB and depth images. For images that have a background, we utilize an existing segmentation network, SAM, along with bounding box prompts, to eliminate the background. More details can be found in the supplementary information. Section Summary. The camera pose estimation in our reconstruction module requires knowing the absolute elevation angle of one camera to determine the relative poses of all cameras. To address this, we propose an elevation estimation module that predicts the elevation angle of the input image by computing the reprojection error for different elevation candidate angles. During training, we generate multiple source view images for reconstruction and utilize ground truth RGB and depth images, as well as a segmentation network for background removal. Section 4.2 Single Image to 3D Mesh. Section 4.2 of this paper presents our unique method of converting a single image into a 3D mesh model, showcasing our approach's effectiveness using both synthetic and real images. We provide a comparison with several existing methods for zero-shot single-image 3D reconstruction, such as Point E, SHAP E, 0123, using the stable DreamFusion version, 3Diffuse, and Real Fusion. Point E and SHAP E, released by OpenAI, are 3D native diffusion models that are trained using millions of internal 3D datasets. On the other hand, the other methods we've mentioned use optimization-based approaches and employ priors from stable diffusion. We've provided visual comparisons in the figures for your reference. We've noticed that while most existing methods are capable of creating reasonable 3D meshes from a single image, there are distinct variations among them, especially in aspects such as geometry quality, fidelity to the input, and the consistency of the 3D models they produce. For instance, methods like Real Fusion and 3Diffuse that attempt to optimize a neural radiance field often struggle to generate high-quality meshes. Point E, which outputs a sparse point cloud, frequently results in meshes filled with holes. Conversely, our method uses a sign distance function, SDF, representation that typically yields better geometric results. When it comes to fidelity to the input image, many existing methods fail to maintain a high degree of resemblance to the original. Although SHAP E shows some improvement in this area, it too has a number of failed cases. Our approach, however, uses a powerful 2D diffusion model to directly generate high-quality multi-view images, instead of depending on 3D space hallucination. This tactic greatly improves the fidelity of our output to the input views, lessens the load on the 3D reconstruction module, and ultimately produces results that are more closely aligned with the input. Several existing methods also encounter difficulties in achieving consistency in 3D output, known as the Janus problem. A contributing factor to this issue is that these methods optimize each view independently to resemble the input as much as possible. Our method differs in that we leverage the view condition 2D diffusion model to inherently improve 3D consistency. We've also evaluated the performance of our method quantitatively, using the Objaverse and Google Scanned Objects, GSO, datasets. To compare the predictions with the actual mesh, we adjusted the scale and rotation, applied the iterative closest point, ICP, technique to sampled point clouds, and selected the most matching prediction. Using these parameters, we've reported the F-score and clip similarity, and the running time on an A100 GPU. As shown in the table, our method outperforms all other methods in terms of the F-score. With regard to the clip similarity, we exceed all other methods except SHAP E. However, we noted that clip similarity is highly sensitive to color distribution and is less discerning of variations in local geometry. In terms of execution time, our method has a significant edge over optimization-based methods and is on par with 3D native diffusion models like Point E and SHAP E. In specific terms, our 3D reconstruction module can reconstruct a 3D mesh in around 5 seconds, with most of the remaining time spent on 0123 predictions, which take about 1 second per image on an A100 GPU. Section Summary. The authors present qualitative examples and comparisons of their method with existing single-image 3D reconstruction approaches. They highlight differences in terms of geometry quality, adherence to the input, and overall 3D consistency. Their approach outperforms baseline methods in terms of F-score and runtime, and demonstrates better adherence to the input views and improved 3D consistency. Section 4.3 Ablation Study. In Section 4.3, we perform an ablation study to analyze the impact of various training strategies on the performance of our model. First, let's discuss the training strategies and the consequences of their absence. When we skip our two-stage source view selection technique and train the network with 32 uniformly posed 0123 predictions, we encounter severe inconsistencies among the source views. This inconsistency results in a total failure of the reconstruction module. If we use only 8 source views without considering the 4 proximate views, the reconstruction process fails to identify local correspondences. This lack of identification prevents the reconstruction of detailed geometric shapes. Similarly, neglecting the depth loss during training also causes the network to fail in reconstructing these detailed geometries. During the training phase, we initially create N renderings of the ground truth. Then, we use 0-123 to forecast 4 proximate views for each rendering. If we rely solely on 8 times the 4 ground truth renderings without using 0-123 predictions during training, the model fails to generalize the 0-123 predictions at the inference stage, resulting in many missing regions. Further, if we substitute N ground truth renderings with N 0-123 predictions, the network collapses due to incorrect depth supervision. Now, let's consider the elevation estimation. The efficacy of our reconstruction module depends heavily on the precision of the elevation angles of the input view. If incorrect elevation angles are provided, say, changing the elevation angles of source views by plus or minus 30 degrees, the reconstruction results are distorted. In contrast, using our estimated elevation angles can perfectly match the results with ground truth elevations. We tested the accuracy of our elevation estimation module by rendering 1,700 images from random camera poses, and as indicated in our results, our module predicts accurate elevations. We also studied the effect of changing the number of source views on the 3D reconstruction. Interestingly, our method doesn't seem to be particularly sensitive to the number of views, provided that the reconstruction module is retrained with the respective settings. Comparing 360-degree reconstruction with multi-view fusion, our method can reconstruct a full 360-degree mesh in a single step, while most existing methods that can generalize neural reconstruction mainly focus on frontal view reconstruction. An alternative strategy could be to infer the geometry for each view separately and then merge them. However, we've noted that this approach often struggles with multi-view fusion due to inconsistent 0-123 predictions. Section Summary. In this section, the authors conduct an ablation study to evaluate the impact of different training strategies on their 3D reconstruction method. They find that their two-stage source view selection strategy is crucial for consistent and accurate reconstruction. They also demonstrate the importance of accurate elevation angles and show that their method is not very sensitive to the number of source views. Additionally, they compare their 360 degrees reconstruction approach with multi-view fusion methods and highlight the challenges of inconsistent predictions in the latter. Section 4.4 Text to 3D Mesh. As the provided figure illustrates, we've skillfully combined our technique with existing text-to-image 2D diffusion models that are already on the market. This combination allows our system to adapt to and handle tasks that involve transforming text into 3D images. Consequently, we're able to create top-notch 3D textured meshes at a rapid pace. For more instances of this in action, do refer to the supplementary resources included. Section Summary. The authors propose a method that combines text-to-image 2D diffusion models with their own approach to generate high-quality textured meshes for text-to-image 3D tasks. This integration allows for the efficient creation of 3D models from text descriptions. Additional examples can be found in the supplementary material.